Today's lecture is part one of earthquakes, or if you prefer, seismic activity. In the interest of saving some video time, I won't go through all the learning objectives. I'll leave that for you to do. But let's look at this. This is a map showing some of the major plates of the world, and what I want you to pay attention to are the arrows, which show the direction that the plate is moving, and the length of the arrows indicates how fast the plates are moving. So if you look at North America, you see that over here in the eastern part of the plate, remember here's the mid-Atlantic ridge and the North America plate starts on the west side of the ridge. So in the eastern part of the North America plate, you see that the direction of motion is basically to the northwest. Then as we move to the west, we see that here, this would be the Great Lakes here, the plate is almost a due west direction, moving in a westerly direction. And then by the time we get over here to the Pacific Northwest area, the direction is to the southwest. So the plate in all places is not going to move the same direction, and the speed will vary across the plate too. And then here we are, the other plate that influences us here in California is the Pacific plate, and you see how long these arrows are. So it's quite speedy in geologic time, at least. It's quite speedy, and it's moving to the northwest. So all this jostling and bumping into each of these plates, bumping and jostling with each other, is going to give us fault lines along which earthquakes can occur. So what causes an earthquake? It's usually associated with the rupture or the slip along a fault line. So as these plates are trying to move past each other, or as faults are trying to move past each other, they can get stuck against each other, and these stresses will begin to build up. So once the stresses build up to the point that the rocks can't handle them anymore, then they are released in the form of what we call seismic waves. These seismic waves end up radiating through the Earth's interior and moving along the surface, and that's what causes the shakes that we feel with earthquakes. The picture that you're looking at on the right-hand side of the screen, that's damage in the Marina district of San Francisco from the 1989 Loma Prieta earthquake, also referred to as the World Series earthquake, because Oakland and San Francisco were playing each other in the World Series at that time. So the most destructive earthquakes are called megathrust quakes, and these occur at subduction zones where you have an ocean plate diving under either another ocean plate or a continental plate. The stresses that build up in this situation, the stresses that build up are capable of producing very high magnitude earthquakes. And by high magnitude, I mean in the 8 or greater than a 9. So those are big time bad. The highest magnitude earthquakes that we have experienced on Earth have all come from earthquakes that occurred in this tectonic setting. Earthquakes can also be caused by magma rising underneath a volcano. All the earthquakes that Hawaii experiences is a result of the magma rising up under Kilauea and Mauna Loa. And some earthquakes can be human-induced. Oroville, hopefully everybody knows where Oroville is. In 1975, after that dam was built up there, which is a really big dam, it's one of the largest in the world, there was a 6.1 magnitude earthquake that happened, and the earthquakes happened along a series of faults that were thought to be inactive at the time. It turns out they had been reactivated by the weight of the water that was impounding behind the dam. So that discovery that this could happen halted the construction on the proposed Auburn Dam, on the North Fork of the American River, because it just so happened that the same system of fault lines was running through that area too. So construction stopped. Other places that have had human-induced earthquakes include in 2007, a major disaster that happened in a coal mine in Utah. When the mine collapsed, it produced a 4.0 earthquake, and the collapse of the mine trapped 6 miners. And after days of trying to dig them out, it just couldn't be done. And another mine collapse happened, and it killed 3 of the rescue workers and injured 6. So it turned out that none of these people could ever be rescued, or their bodies couldn't be recovered from the mine. So the mine became their grave. Then in Denver, the Denver area, in 1962, there were some crews at the Rocky Mountain nuclear arsenal that started injecting radio wastewater into the ground. And just a few months later, Denver started experiencing all of these earthquakes. One of them caused over $1 million in damage. So everybody was trying to figure out, Denver isn't subject to a lot of earthquakes, so what's going on here? Well, it was determined that those earthquakes were being caused by the disposal of that water, and that this was the first recognized case of what we call induced seismicity, and it's humans that are inducing it. And we see that more and more and more in Oklahoma, Texas, Ohio, into Colorado, all these areas where fracking for fossil fuels is going on. They are experiencing this phenomenal number of earthquakes. So this is California. These are the major fault lines running through California. And we see that the San Andreas Fault, again, the San Andreas Fault is the boundary between the Pacific Plate and the North America Plate over here. And there are probably thousands of faults associated with this. Some of them we don't even know about until an earthquake occurs on them. But there are some major ones, like the Hayward Fault, the Calaveras Fault, the Rinconda Fault down here. All of these are related to this movement along between the North America Plate and the Pacific Plate. So we should just refer to this as the San Andreas Fault Zone rather than just the San Andreas Fault. We've got the Death Valley Fault over here, the Panamint Valley Fault. These are related to that stretching that's taking place in the basin and range, that divergence that's going on here. So we're just full of faults, no pun intended. And again, this is another view of the major faults here. This is the Hayward Fault. Hayward is on this fault. Berkeley is on the fault. Oakland is on the fault. When it goes underneath San Pablo Bay right here, it comes out on the other side, and it's called the Rogers Creek Fault. Then over closer toward us, there's the Green Valley Fault that is near Vacaville. And it's thought that this was the fault that caused 2 major earthquakes in the late 1800s that basically destroyed what was then Vacaville, and also my town of Winters, where every year in August there's an earthquake festival to commemorate the damages that, it's odd to commemorate damages, but to commemorate that earthquake. So if it's happened once, you know what we say in geology, if it's happened once, it can certainly happen again. All right, some important terms to know when we're talking about earthquakes are focus. Focus is the point of origin inside the earth of the earthquake. That's where the movement has occurred along the fault line that is initiating the earthquake. The epicenter might be a term that you know better. It's the point directly above the focus on the surface. So whenever we know or we hear about an earthquake, we always want to know where the epicenter is. Normally, we want to know that because that's where the most shaking is going to be, and that's where the most destruction is going to be, but not all the time. And we'll talk about some of the exceptions to that later on in this lecture. So a foreshock is the shaking of the earth prior to big event. Sometimes the foreshock, we might not know it's a foreshock until something of a larger magnitude occurs. Then an aftershock, those are the earthquakes that occur after the big event. A seismic gap, that's a red flag to seismologists. Because that's an area along a fault where there's been no movement. That means that stresses are building up. And maybe they've been building up for 100 years, 150 years, maybe even 300 years. So you know that when that fault lets go, that there are going to be all these stresses that are going to be released then, and probably a higher magnitude quake will be the result. Sometimes these seismic gaps are caused by asperities. An asperity is an area along the fault where these two sides of the fault are stuck against each other for some reason. Maybe it's the type of rock that's there. Maybe it's just that the stresses haven't built up enough so that it's going to move. One of the more famous ones is along a section. Well, I'll show you a map of that a little bit later. But they're in an area known as Parkfield, California, a little tiny area down in Central California. Earthquakes occur there on a fairly regular basis. That's where we have the San Andreas Fault Observatory at Depth, or SAFOD for short. And it was put there, this hole was drilled into the fault where all these instruments have been put into the ground. It was done there because of the regularity of the faults that occur. What's going on there that of the regularity of the earthquakes that occur. Sorry, I'm getting ahead of myself. What's going on there that causes earthquakes to occur on such a regular basis? Well, it turns out that there's in that area where the earthquakes are happening, there's a belt of talc. Talc is a mineral that's associated with serpentinite, our state rock, and it's slick and greasy. So the faults, two sides of the fault are apparently able to move past each other on a nice regular basis. And then a seismologist, that is the scientist that studies earthquakes. Size, anytime you see that word seismograph, seismologist, seismology, seis is a Greek word for shock. So these scientists that study these shocks, waves that are moving through the earth. So what is the theory behind how earthquakes occur? Well, this wasn't known until after the 1906 San Francisco earthquake, when people didn't even know that there was a fault, that there was a San Andreas fault there, until those damages started being mapped out. And then they were showing up in this nice linear fashion. And then at that point, I guess they thought, wow, there must be a fault here. So there was a geologist that proposed this is how it occurs. He said that rocks can be elastic, and especially as friction builds up, as the two sides of the fault are trying to move past each other. So the rocks can be stretched as a result of that. So on the ground, we might see that with deformation of anything that might be at the surface. At some point, though, those rocks get stretched past their elastic limit, and all the stresses that have been building up between the two faults get unleashed then in the form of these seismic waves. So with the fence there, we see that it broke. Well, afterwards, the rocks will return to their original shape, but they're in a totally different location. So that's called the elastic rebound theory. And we still use this today. There have been some clarifications and some perfections to this, but it's still the same basic idea. Rocks are stretching, and they get stretched past their limit, and then they got to give way to release all of the pressure and stresses that have built up. So where might we see that represented? Well, one of the great places that we can go to, and we were going to go to, but now that all this happened, we won't be able to, is Point Reyes. Point Reyes, the Point Reyes Peninsula shouldn't be where it is. It's hitched a ride northward along the San Andreas Fault. So in the 1906 earthquake, there just happened to be a fence that was atop the boundary, atop San Andreas Fault. And one part of the fence moved from 16 to 20 feet to the north, and that's what you're looking at over here. That's the Pacific plate here, and this is the North America plate over here. So Pacific plate is moving, whoops, sorry, that is totally not right, is moving to the northwest, and the North America plate is moving kind of in a westerly position, or a westerly direction, so they kind of rub up against each other. And had that fence not been there, we wouldn't see such a obvious representation of what is happening during an earthquake. But it's been rebuilt many times. People like to go and say they have 1 foot on the Pacific plate and 1 foot on the North America plate. It's probably not that simple. It's more like a zone here, but anyway, if that's how people want to remember it and think about it, that's fine, because it certainly sticks in your brain. So that's the fence. But if you want something a little bit more spectacular than a fence breaking, how about this? This is Pinnacles National Park. It used to be a national monument. It's one of our newer national parks. It was signed into a national park by President Obama. And these rocks don't belong here. It's part of an old volcanic system that, again, has gotten a ride on the movement of the San Andreas Fault. It's actually moved about 200 miles from its mate, from the other part of the volcano. It's about 200 miles to the south, near Gorman. So for 23 million years, every time there was an earthquake, maybe the fault was creeping at some point. Maybe there was a big earthquake and there was a lot of movement, or there was just a tiny earthquake and there were just inches of movement. But over that 23 million years, the rocks have moved 200 miles to the north. And this is the anatomy of the Loma Prieta earthquake. Again, I want to note to you here the San Andreas Fault. Let me get the laser pointer or this pen. One of these days I want to figure out how to use it. Here's San Andreas Fault. So the epicenter of the quake was in the Santa Cruz Mountains, Loma Prieta. And this is where textbooks lie to you, because we're talking about the San Andreas Fault. We know that it's a strike-slip fault, meaning that it moves horizontally against the North America plate. It's moving in a horizontal direction along the strike of the bedrock. But it also has, Mother Nature is messy. She doesn't always do things the way we think she should do them. She's messy. So there was also a vertical component to that. So the lateral slip was about 6.2 feet and the vertical slip was 4.3 feet. So it jumped up 4.3 feet and moved horizontally 6.2 feet. Now, think about that. The Pacific plate is one of our larger plates. So for that whole plate to move like that, you know that there's going to be a lot of shaking going on. And there was. That earthquake was a 6.0, I always get these mixed up, a 6.9 magnitude quake. And these are some of the damages that it caused. This was one of the places where there was a lot of injuries. It could have been worse, but again, a lot of people had tried to get home early to see the baseball game. But this was the Nimitz Freeway, and sections of this double-decker freeway pancaked down on the bottom sections. And there was, I think, 30-some people that were killed in this. And this is why we will have no more double-decker highways in California. And then the East Bay Bridge, one of the upper sections fell into the lower section. So this is why the East Bay Bridge had to be rebuilt. into two spans. That's a picture of when it was being built. This is what it looked like after it was built. The construction lasted from 2002 to 2013 on this thing. The original estimate to build it was $1 billion. Well, that didn't quite pan out. The estimated total cost was about $6.5 billion. So that was quite a cost overrun. All right, so what about these seismic waves then? There are two types. There are body waves. They're the ones that move through the interior of the Earth. They're the fastest moving ones. They come in two types. There's a P wave, which is short for primary wave. It's the first one to arrive at a particular station. And then there's the S wave, or the secondary wave. The P waves move by expansion and compression, and the S waves move like the snapping of a rope, the wiggly look that you get. Then the surface waves are slower. They travel along the surface of the Earth. They're the big damage makers. They come in two types, the Love wave and the Rayleigh wave. So let's look at the P waves first. The P waves cause the ground to have vibrations along or parallel to the direction of the wave. And if you look at the little video to the right, you see what's happening. The rocks expand and compress. The rocks are being expanded and compressed, kind of like a slinky, if you remember the old toy slinky and how it works. So this is the fastest of the waves, the first one to arrive at a point away from the epicenter. They can travel through rocks, they can travel through fluid, and their typical speeds will vary depending on whether it's in air, in water, or in granite. If it's in air, they travel at about 330 meters per second, in water at about 1,450 meters per second, and in granite at about 5,000 meters per second. So some people say that they hear the earthquakes, and there might be something to that because sound wave moves by expansion and compression too. Sometimes these things are moving so fast that they blast out of the ground, and they can cause expansion and compression in the air. So that might be what people think that they're hearing. Then the secondary waves. The motion causes the motion of the ground to be perpendicular to the direction of the wave. So you can see what's going on here. See the wavy-like motion? So kind of like the shearing of in fact, they're called shear waves. So kind of like, I don't know how to explain it except for the snapping of a rope and the wiggles that show up in the rope, this wavy-like motion. These can only travel through solids. They cannot travel through liquid. This is how we know that there's a liquid outer core, because secondary waves will not move through the liquid outer core. I always explain it, scissors. You know, scissors shear things. Have you ever tried to cut water with scissors? No, you can't do that. Water refuses to be sheared. So they can't travel through liquids. The speed is about 60% of a P wave in a material, and they are the second waves, hence the name, secondary waves. They're the second one to arrive at a point away from the epicenter. All right, what about the surface waves? The surface waves, let's look at the Love waves. Look at what's happening. If, let's say we have a brick foundation or a brick fireplace or a brick wall, and a Love wave impacts it. This is what will happen to the bricks. They're shifted away from each other. So a Love wave has this back and forth kind of motion to it. That causes things to shift here horizontally in this back and forth kind of way. They're slower than the P waves and the S waves, but they are faster than the Rayleigh waves. And they're named for A.E.H. Love, who was the man who predicted that type of seismic wave in 1911. So if you've ever seen videos of an earthquake and you see like chandeliers moving back and forth, that's the love wave. Or maybe things have been tossed off shelves, that's the love wave doing its thing. Then the surface wave, again, the second type of surface wave is the Rayleigh wave. They cause a rolling motion, like an ocean wave. If you are standing on the beach and you're watching these waves roll in toward you, this is how the Rayleigh waves move also. Some people describe during an earthquake, they're on the road and it's like the road is rolling toward them. Well, the road isn't really rolling toward them. That's the energy wave that's moving through that makes it seem that way. So these are the slowest of the seismic waves. They travel at about 3 kilometers per second, and they are produced by the interaction of the P and the S waves at the Earth's surface. And we can use Rayleigh waves to characterize, again, the Earth's interior and oil deposits. This is the type of seismic waves that oil companies use to look for oil deposits. So seismic waves, all the seismic waves are going to depend on, the intensity will depend on what's the size of the earthquake. How far away are you from the earthquake? So distance to the earthquake. How deep is it? Usually the deeper the earthquake, the more time that the waves have had to moderate themselves. So the damages at the surface might not be as great. And then what's the geologic structure of the crust? The amplitude of the wave the amplitude will decrease with increasing depth of the earthquake and with distance traveled. So again, primary waves, the body waves, the primary waves, the focus is at the focus. That's where they start. The surface waves, Rayleigh waves, and love waves, the source is going to be at the epicenter. So this is a typical seismogram, except it doesn't show the surface wave. And that's for a reason, because I want to tell you how these are used to determine where the earthquake occurred. Where was the focus? Where was the epicenter? So the first wave to arrive at a seismic monitor will be the P wave. And then depending on how far away the earthquake is from the seismic monitor, the S wave will arrive. If we're lucky and the monitor is set up right over the focus, then these P waves and S waves would get there almost simultaneously. So it'd be really hard to pull them away from each other. But at some interval after the arrival of the P wave, the S wave will arrive. The greater the interval between the arrival of the P and the arrival of the S, the greater the distance to the earthquake source. And we can use the difference in arrival time, the interval between arrival times, to determine how far away the earthquake was. These are just some diagrams showing the secondary wave, what it would do to material that it's moving through. And then there are shadow zones. In the 1960s, we started a network of seismographs around the world because it really wasn't to look for natural earthquakes. It was to make sure that countries were adhering to the nuclear test ban treaty. But it turned out that seismic network had another benefit, and that was scientists were able to just study thousands and thousands and thousands of earthquakes. So we realized that there are shadow zones depending on where the focus of the earthquake happens. So for this particular example, the focus is up here at the North Pole. I don't know how many earthquakes occur at the North Pole, but just for this example, here we go. So this is these are the P waves, and you see that they hit the inner core. I'm sorry, that's the outer core, Lisa. They hit the outer core, and they're kind of deflected away from the outer core. Then that's kind of deflected away, but here it's refracted. Here they're well, okay, I'm getting tongue twisted here. Refracted. So we know that there will be a shadow zone right here. If there's a seismic monitor set up in this region, then it's not going to be able to detect the P wave. So we call that the shadow zone. Then with S wave, see what happens here. Same focus. Here it comes, and there's the liquid outer core, and it just does not move through. It's not refracted by it. It's just kind of deflected by it. It's not going to move through. So look how much larger that shadow zone here is here. Well, if you have a seismic monitor set up where there's the overlap between the P and the S wave, you're not going to detect any of those. So you would have to wait, that monitor would have to wait until the surface wave got there before anybody looking at it would know that there's an earthquake that had occurred. So we have these shadow zones mapped for no matter where an earthquake happens on the globe. And by the way, that seismic monitoring network, we're in like the 3rd generation of these seismic monitors now, so they're pretty darn sophisticated. So the Rayleigh waves and the Love waves, these are the big damage makers, with the Love wave causing the most damage. There's that rolling oscillating motion, and there's that shifting horizontally side to side. Now, this is a perfect seismogram here. Here's the arrival of the P wave, here's the arrival of the S wave, and then over here, and the wave with the highest amplitude. Amplitude is just a word that means height. The wave that will have the highest height at a seismic monitor will be the surface wave. So these two waves, should I try my pen once more? These two waves right here, we need to determine how far away the earthquake occurred from a particular station. The surface wave, the wave with the highest height, we use that to determine what the magnitude, one of the ways that we determine what the magnitude of the earthquake was. So a seismograph is the instrument for recording seismic events, and a seismogram is the written record of the seismic event. I won't play this, but this is my favorite group now, the Amoeba people. This is their seismogram, their seismograph song. So check it out. They mimic the motion of the P wave, the S wave, the Rayleigh wave, and the Love wave. All right, so how do we find out where the epicenter of the quake is? It's a method that we use in surveying all the time called triangulation. In order to determine where the epicenter of the quake is, we have to have 3 records from 3 seismic stations. So what happens is we use this, I'll go back and forth between these, but a graph like this. Now, everything is so automated these days that as soon as an earthquake occurs, you can go to these real-time earthquake websites like the USGS, California earthquakes, hit a button, and you know just about everything there is to know. But, you know, we had to have analog type of data before we got to this digital world that we're in now. So I want you to understand how we got to that point and how we used to have to do this. This is called a travel time graph, and it shows what happens at particular distances from an earthquake. So let's say that we had a station set up in this location right here. Well, that location would show that the P wave got there 5 minutes, took the P wave 5 minutes to get to that station. This same station then would show that the S wave got there 9 minutes after the earthquake occurred. So we look at the interval here between, where did I go here? Between 5 minutes and 9 minutes, and it's 4 minutes. So if we calculate that there was a 4-minute interval between the arrival of the first P and the arrival of the first S, then we know that that earthquake was 1,500 miles away from us. So we would use data like that. Let me go back to this. So that station showed that it was 1,500 miles away. Well, these stations show the earthquake was 2,800 kilometers away from that particular station. Then over here, the earthquake, the travel time graph showed that the earthquake was 4,800 kilometers away. And here at this station, the travel time graph shows that it was 3,400 kilometers away. So we would draw circles with a diameter of 2,800 miles, 4,800, sorry, that's kilometers, 4,800 kilometers and 3,400 kilometers. Where those circles intersect, that's the epicenter of the earthquake. That's where the earthquake occurred. So again, 3 stations to do that. Again, all this is automated these days because of this very sophisticated system network that we have in place around the globe of seismic monitors. But the old-fashioned way, using the travel time graph. So when an earthquake would occur at a particular station, you would have somebody with these graphs in hand showing, plotting the time of arrival of each of these waves. And again, these are the body waves, the primary wave and the surface wave. We need those, specifically the interval in arrivals between the two. We need those to determine how far away the earthquake was from a particular station. And you can see what's happening with this graph. The farther away we get, the greater the interval is going to be between the arrival of the P and the arrival of the S. So that is triangulation. We've got to have 3 stations. So these are some pictures showing what happens when things move, when the love wave comes to town. This is in the 1994 Northridge earthquake. Some of the fastest horizontal ground motion ever recorded in an earthquake was recorded here. So you had a lot of buildings that were just kicked out, and in particular, this building has been shifted out, and there are cars landed on cars that were parked outside the building. A lot of buildings had what are called soft first stories, and they were all damaged. That was where most of the damages occurred in this earthquake. Here's another view of what happened. So that's horizontal ground motion. A lot of the hospitals were heavily damaged. You had people that needed to get to emergency rooms, but the hospitals were damaged. So California ended up enacting legislation where if there were hospitals that had trauma units associated with them, they had to be seismically retrofitted to be able to withstand some of these earthquakes that we experience here in the state. So ground motion during earthquakes. I'm going to stop my lecture here. We'll take a look at this in part 2. So I'm signing off for now. Goodbye.